In section 8.5, we're going to look at some more convergence tests. Again, keep in mind, with all of these tests, our whole purpose is just determining whether a series converges or diverges. That is, would have a finite value or goes off to infinity. We won't be able to determine the actual sum of the series. We're going to look at kind of 3, but really 4 tests here. The ratio test, the root test, and then there are actually 2 comparison tests in this section. So we'll start with the ratio test. If the series sum of a sub k is an infinite series with positive terms, we'll define R as the limit as k goes to infinity of a sub k plus 1 divided by a sub k. If R is between 0 and 1, the series converges. If R is greater than 1, including the infinite case, the series diverges. And if R equals 1, the test is inconclusive and we basically have to try a different test. So let's give it a shot. One quick thing to note, because one of the things that you'll need to be able to do when you look at series in the future is to pick one of these many tests that we have. And this test is particularly useful when the series contains a factorial term. Okay? It's not the only time you can use it, but when you have a factorial term, you'll often use this test. All right, so our first one actually does contain a factorial, and here we go right away. I would like to use the ratio test to decide whether the series k to the 6th over k factorial converges or diverges. So I'm going to define my R just like this. It's the limit as k goes to infinity of, first of all, a sub k plus 1. Just plug k plus 1 in for the k's. So k plus 1 to the 6th over k plus 1 factorial. That's divided by a sub k, which is k to the 6th over k factorial. Dividing, I'm just going to write that as multiplied by the reciprocal. So times k factorial over k to the 6th. All right, let's see here. How I write this next step is going to be key in my being able to evaluate this limit. These two things that are both to the 6th power, I'm going to combine them in one fraction. K plus 1 over k, all to the 6th power. Times, the numerator has a k factorial. And now, what I'm going to do with this k plus 1 factorial is going to help a lot. We know that to evaluate k plus 1 factorial, I would just multiply, right? It would be k plus 1 times k minus 1, and so on. The rest of this would actually just be k factorial, right? K plus 1 times all the factors from k on down, which by definition is k factorial. That, of course, is really nice because it allows me to divide out the k factorials. So I think I'm just about there. This says k goes to infinity. If we use L'Hopital's rule just on this little bitty piece in here, that's really infinity over infinity. And using L'Hopital's rule, that would just become 1 over 1 to the 6th power times, the second fraction is a 1 over, k plus 1 is now going to be infinity plus 1. That's 1 times 1 over infinity, which is 0, or 0. So r is 0. That puts me in this first case. My series converges. And in this case, I would say it converges by the ratio test. All right, let's try another one. And by the way, we're actually not going to do C. C is much better done by the root test, so not going to do that one. We can use all of this space, and we're probably going to need it. Again, with a factorial in here, I know that the ratio test is probably my best bet. So let's define our r as the limit as k goes to infinity. And first of all, I would have a sub k plus 1. So I'm going to replace the k's with k plus 1s. So k plus 1 factorial squared. And at the bottom, 2 times k plus 1 all factorial. Divide that by a sub k, the original, k factorial squared over 2k all factorial. And so, what have I got here? The numerator, k plus 1 factorial squared, could be written as k plus 1 factorial times itself. The denominator, I'm just going to distribute the 2k plus 2 factorial. Then I'm going to say let's invert and multiply. So the reciprocal here, 2k factorial. And again, I'm going to write that as k factorial times itself for the square. All right, I'm going to use the same little trick that we did on the last problem. These guys, I'm going to rewrite each one of them as k plus 1 times k factorial. And again here, k plus 1 times k factorial. Same trick as the previous problem. I'm going to use a very similar trick on the denominator. This would be 2k plus 2 times 2k plus 1, and then it would be 2k on down, or 2k factorial, times the second fraction here, and by all of that judicious rewriting, we've got some nice cancellation that's going to happen right here, right? We would have our k factorial canceling there and there, and we'd also have our 2k factorial canceling there and there. So what I've got left is just k plus 1 times k plus 1 at the top, which would be k squared plus 2k plus 1. And at the bottom, 2k plus 2 times 2k plus 1 is 4k squared plus 4k plus 2k would be 6k plus 2. All right, that is definitely an infinity over infinity case, which I could handle by L'Hopital's rule. Derivative on top is 2k plus 2. Derivative on the bottom is 8k plus 6. Oops, that was a k, not an x. Still infinity over infinity. And so if I use L'Hopital's rule one more time, derivative on the top now is 2, and on the bottom is 8. So I'm just going to get a fourth. Once again, if you look back up at the box at the top of the page, that 1/4 is definitely less than 1. And so that puts us back into that convergent series situation. So we're going to say converges by the ratio test. All right, so that's our ratio test. Again, you can use it anytime you want to try it, but it's primarily the most useful when we've got factorials involved. Our second test in this section is called the root test, and it looks like this. Again, if the sum of a sub k is an infinite series with non-negative terms, we're going to define rho as the limit as k goes to infinity of the kth root of a sub k. And essentially the same results here. If rho is between 0 and 1, our series converges. If rho is greater than 1, including infinity, the series diverges. And if rho equals 1, our test is inconclusive. We'd have to use another test. This test is particularly useful when the series contains a term with k in the exponent. So we use it real often when the k is in the exponent of our original series. Okay? You'll notice that happens in both of the examples on this page. So this first one, the sum of k to the k over 2 to the k. I'm going to say rho then is the kth root, it's the limit. Let me fix that and make it squeeze it in. It's the limit as k goes to infinity of the kth root of a sub k. Our a sub k is k to the k over 2 to the k. So that would be the limit as k goes to infinity. And of course, taking the kth root of the kth power just gives me k on the top and 2 on the bottom. Well, as k goes to infinity, I get infinity divided by 2, which is certainly infinite. And since rho is greater than 1, including in this case our infinity case, I would be able to say my series diverges by the root test. All right, let's try one more. In B, we have the series k over e to the k. Now the denominator still has k in the exponent. I think the root test is a reasonable try here, so let's go for it. Once again, our rho is the limit as k goes to infinity of the kth root of this term, k over e to the k. Now the top doesn't come out quite as well this time. Kth root of k I'll just kind of leave there for now. but the bottom comes out really well. The kth root of e to the k would just be e. This e in the denominator, I'm going to pull that out in front of my limit. And the kth root of k could also be written as k to the 1 over k power. I'm going to take this limit and just kind of do it off to the side here, and then we'll finish out once we have it. In order to do this limit, because it is going to be an infinity to the 1 over infinity or 0 case, that's an indeterminate form, but it's not a L'Hopital's rule form yet. Remember what we talked about earlier this semester. When we have these exponential indeterminate forms, we usually need to use that trick of taking the natural log. So let me say, let's define L as the limit as k goes to infinity of k to the 1 over k. Then the natural log of L would be the limit as k goes to infinity. And when I take the natural log here, I'll be able to bring that 1 over k down in front. So 1 over k, ln k. This is an infinity over infinity case. So I'm going to use L'Hopital's rule here. The derivative of ln k is 1 over k. And at the bottom, the derivative of k is 1. I keep doing that. That's the limit as k goes to infinity. Sorry. So ln L equals 1 over infinity, which would be 0 on the top, over 1 on the bottom. Natural log L equals 0. And if I exponentiate both sides, L equals 1. So this whole limit turned out to be 1, giving me a row value of 1 over e. 1 over e is less than 1. And so my series converges by the root test. All right, so there's two of them, ratio test and root test. Let's talk next about the comparison test. Here's the statement. Let a sub k and b sub k series be infinite series with positive terms. If b sub k converges, and the a sub k's are less than the b sub k's, then the a sub k series also converges. If b sub k diverges, and the a sub k's are bigger than b sub k's, then the a sub k diverges. A lot going on there. We're going to unpack it in just a moment. But let me outline the process first. Essentially, the a sub k's are going to be the given series. And the b sub k's are going to be a series you pick. You're going to try to choose a series that's either greater than or less than the original based on what you think is going to happen, right? If you think you're going to get a convergent series, then you would have picked the b sub k's bigger than the original. If you think that you're going to get a divergent series, then you would have picked them smaller. So, in other words, you want your b sub k's to be, or let me say it the other way around. You want the a sub k's smaller than a convergent series. And in this case, you want the a sub k is bigger than a divergent series. If we think about that for just a moment, hopefully it makes sense. If I have something that I know converges, and I've got numbers smaller than that, if it's smaller than something that already converges, it's got to converge. Conversely, if I have something that I know diverges, and my numbers are even bigger than that, then they must also diverge. So, our goal here, and the trick to this, is always going to be picking a good series for the b sub k. So you're going to need to choose an appropriate b sub k to compare to. This next sentence is important. If possible, try to choose series whose convergence or divergence is simple to determine. You don't want to have to work too hard with your b sub k. What kinds of series do we already know really easily whether or not they converge? Geometrics, those are easy, right? They converge if the absolute value of r is less than 1. Harmonic, that always diverges. P-series, this one converges when p is greater than 1. Let's just jot those down for ourselves. The geometrics, a r to the k, those converge if the absolute value of r is less than 1. P-series, the 1 over k to the p, those converge for p greater than 1. The harmonic is just a special case of the p-series where p equals 1. Harmonic always diverges. So in an ideal world, I would like to pick my b sub k to be one of these, because I already know whether they converge or diverge. Let's give this a shot. So in my first example here, example 3, the series whose convergence I'd like to determine is ln k over k cubed minus 1. Now, this is not really a p-series. ln k can't be part of the p-series. But with a k cubed on the bottom, I kind of think it probably converges because I've got a p greater than 1. I still have to prove it because it's not a true p-series, but it makes me suspicious that this is probably convergent. Okay? So since I think it's going to converge, what I want to do is I want to pick a b sub k bigger than it, but that also converges. Okay, so I'm going for this. This is less than or equal to the series from 2 to infinity. And now let's make a fraction that's bigger. How do you make a fraction bigger? Well, you can make a fraction bigger by either increasing the numerator or decreasing the denominator, right? All right, let's start with increasing the numerator. The natural log of k is always less than k itself. So that would be one way to increase the numerator. Oh shoot, I picked a bad example. Do me a favor, change this one. Would you please make that a k cubed plus 1? The limit comparison test will help us deal with when it's a minus 1, but for right now I want to use this one. Decreasing the denominator here, I could just make it k cubed. That would make the denominator smaller. That's pretty nice because that simplifies really well. K over k cubed simplifies to 1 over k squared. This is a p-series, and it converges because p is 2. So I've done exactly this, right? My AKs, the original series, are smaller than a series that I now know converges. Therefore, I can conclude that the original series also converges by the comparison test. All right, let's try another one. This is a bit of art. You have to just kind of get used to picking these comparison series. That takes some practice. Just doing more problems will help. Let's try this next one. This time I've got the series square root of k over k cubed plus 1. Now once again, I always try first thing to sort of think, hey, do I think this is going to converge or diverge? So this is what's going through my head. The 1's not particularly important. So this is kind of like, what would that reduce to? 1 over k squared, but under the radical? The square root of 1 over k squared is 1 over k. 1 over k is harmonic and diverges. So I think this is going to diverge. Since I think it's going to diverge, back up here again for a second. I think it's going to diverge. I want my given series, this is my a sub k's, to be larger than something that diverges. All right, so if this is going to be larger than this, I'm trying to make this smaller. So same deal with my fraction under the radical. My goal is to make that fraction smaller. And I know I can make a fraction smaller either by decreasing the numerator or by increasing the denominator. So let's see. Decreasing the numerator, I don't really even have to do that. I could just keep that as k because it's greater than or equal to. That's not going to hurt anything. I do have to increase the denominator, if anything, and that 1 is causing me trouble. I can't simplify as long as the 1 is there. So I'm going to leave the k cubed. And then the way I'm going to make the denominator bigger is just by changing that 1 into a k cubed, right? K cubed is certainly bigger than or equal to 1. So I've made my denominator larger. That makes the overall fraction smaller. So I've really got the square root of k over 2k cubed. That square root of 2 in the denominator, I can just bring that up in front. And then the k over k cubed would simplify to 1 over k squared. The 1 over square root of 2, I can pull that out of the whole sum. And the square root of 1 over k squared is just 1 over k. And of course, I now recognize that as a harmonic series, meaning it diverges. So, my original series is bigger than something that diverges. That means my original series also diverges by the comparison test. The trickiest part of the comparison test is to get the inequalities to go in the right direction. Again, just to review, in order to make the conclusions that you want to make, a convergent series has to be less than another convergent series. A divergent series has to be greater than another divergent series. So less than a convergent or greater than a divergent. The other way doesn't help a bit. If my series was less than a divergent series, it doesn't tell me anything. Got to be greater than a divergent or less than a convergent. All right, the last test is actually going to help us out with things like I kind of almost fumbled on that first one when that really was a -1, and I said, ooh, it's a little hard to make the denominator smaller there. The limit comparison test, the last of the 4 in this section, is going to take away some of those little small trivial things and help us to just look a little bit more at the big picture. I usually find this one a little bit more helpful. So once again, we're going to have 2 series. The given one, the a sub k's, and then the b sub k's, the ones that you're going to choose. If they're both infinite series with positive terms, and they satisfy the property that the limit as k goes to infinity of a sub k over b sub k equals L, then if L is really any finite value between 0 and infinity, then the 2 series behave the same way. Either they both converge or they both diverge. If L is equal to 0 and your B's converge, then your A's will also converge. If L is equal to infinity and your B's diverge, then your A's will also diverge. Notice there are a couple of cases that this does not handle, right? If L is 0 and B diverges, we don't know what happens. If L is infinity and B converges, we don't know what happens. So there are a couple of inconclusive cases here. Now again, you're going to choose your series, B sub k, in a very similar way as we were doing with the comparison test. But the nice thing here, we do not have to mess with getting those inequalities to go the right way like we did before. Everything's taken care of in this limit. So, let's take a look here at a couple of examples. In example 4, I've got the series that adds up a whole bunch of algebraic fractions. I know in my head that this fraction is really governed by the highest power in the top and the bottom. So in my head, I'm kind of thinking, just look at the k squared over k to the 4th. That would simplify as 1 over k squared. That's what I'm going to use for my comparison. So these are my a sub k's, the givens. I'm going to choose to let b sub k be 1 over k squared. Again, the reason I looked at those highest powers, and then just simplified. Limit comparison test says I need to find the limit as k goes to infinity of a sub k over b sub k. If it's okay with you guys, just to save a little time and space, instead of dividing by 1 over k squared, I'm going to multiply by k squared over 1. So I'm just saying times the reciprocal. That's going to give me the limit as k goes to infinity of k to the 4th plus k cubed minus k squared over k to the 4th plus 4k squared minus 3. Definitely the infinity over infinity case. I could do L'Hopital's rule, but with that 4th power, it's going to take about 4 derivatives to get there. So I think I'm going to do a throwback here to Calc 1. Remember the little process where we sometimes divided the top and the bottom by the highest power? In this case, k to the 4th. If I do that, this is going to become 1 plus 1 over k minus 1 over k squared. And that's 1 plus 4 over k squared minus 3 over k to the 4th. And as k goes to infinity, each of these fractions will have infinity in the denominator. So they're all going to go to 0. So I'm just going to end up with 1 over 1. Or 1. Since 1 is definitely between 0 and infinity, these two series are going to behave the same way. They're either both going to converge or both diverge. But notice the B is nice and simple, right? This would be a convergent P series. So since 1 over k squared is P series, P equals 2, and it converges, and with an L of 1, we know that the given series also converges by the limit comparison test. All right, let's try one more. On this last one, our series is 1 over 3 to the k minus 2 to the k. In a case like this, I'm thinking of this as probably going to be geometric, and the problem is the two different terms are going to cause me trouble. So what I'm going to do is I'm going to go with the one that's the higher, or the larger value. I'm going to ignore the 2 to the k, and I'm going to say let's let the b sub k's, the comparison series, just be 1 over 3 to the k. Okay? So here's my a case. I'm going to choose bk to just be 1 over 3 to the k. I'll note to myself that series could also be written as 1/3 to the k. And that's a geometric series with an r of 1/3. So this guy converges. Right? So I'm going to do my limit comparison test. And as long as I get an L between 0 and infinity, I know that since this guy converged, my original would also converge. Let's do the limit comparison test, and hopefully that happens. So I got to take the limit as k goes to infinity of the a sub k over b sub k. That's our L. A sub k is the original. 1 over 3 to the k minus 2 to the k. And I'm supposed to divide by this, but again, just to save us a little time and space, I'm going to go right ahead and just multiply by the reciprocal. Of the b sub k. All right, so I get 3 to the k on top over 3 to the k minus 2 to the k. I'm going to use a little modified version of dividing by the highest power. I'm going to still divide, but by the highest value. I'm going to divide top and bottom by 3 to the k. So on the top, 3 to the k divided by 3 to the k is 1. On the bottom, 3 to the k divided by 3 to the k is still 1. And this is going to give me 2 divided by 3 to the k. This fraction, since it's less than 1, goes to 0 as the power goes to infinity. So I just get 1 over 1 or 1. And once again, with an L of 1, L is definitely between 0 and infinity. And since my comparison series converged, my original series will also converge. All right, that brings us to the end of 8.4, or excuse me, 8.5. We have just one section left to finish up Chapter 8.